All right, so let's start. Thanks everyone for joining for today's session. I am Alejandro Primera, and this is part of the sessions that we're doing for a community of enthusiasts of on Python, people that would like to learn Python from scratch or have an intermediate or advanced level. So we are sharing a lot of information through these sessions, and we also appreciate anyone coming and doing any particular presentation on any work that you may have done. So the sessions have been mainly organized and sponsored by OpenSim Technology through Primera Resources. And we are mainly organizing and distributing a lot of the codes open source through these sessions. Today we're going to talk about continue talking about Volve. I hope that you had a chance to have a look at the presentation that we put together last time. Ankit had a very good session showing the Volve data, and he also made an interesting exercise about petrophysical interpretation. And I have finished the exercise with some information from well deviation surveys from some reports. So the ambition for today, it's go revise the deviation survey now from the real-time data. So it's that shouldn't take us a lot of time. Once you figure out how to read it, it's not that difficult. And then we'll go through reading production logs. And at the end, we will also read some of the pressure data from the measure while drilling information. And at the end, I'll try to put everything together, integrating petrophysical interpretation, production log, and also pressure information into a common, let's say, canvas with all the petrophysical interpretation and all this other data, right? So let's start with this one. So deviation survey from WITSML. I hope I'm not missing anything, but let's crack on straight away. So before I show you, before we land into the coding, let's explore a bit of what we have in the Volve directory. I hope you can see my files, but what you have is a lot of folders with the WITSML real-time information data, and this is effectively distributed in a bunch of subfolders. So let's take, for instance, this well. So we have quite a few folders, and the one that I'm interested at the moment is the trajectory folder. And in the trajectory folder, you have quite a few XMLs. So XML is it's just a format that organizes the data in a three-level sort of organization. So I'm going to show you the file. The file is a bit messy, but if you see the file, it's pretty much flat out with the nodes, different nodes. So I hope you can see. I don't know if you can see on the. I know it's a bit tiny, but on the right-hand side, we have the actual nodes of the file, and I'm using Notepad for this, and I'm using a plugin in Notepad called XML3 Viewer, XML3 View. So, but inside that file, we have different trajectory stations, and if you have a look, we have a measure MD. Just a second, we have a message or something. We have a measure data, TVD, inclination, azimuth. Unfortunately, I cannot zoom in this file, but I'll zoom when I have a chance on the rest of a break. So, but this is just to show you the file, more or less how it's organized. What I'm going to do now, it's go straight to Python. and start to see what we can do with that file. Just if you allow me just 1 second. I have this empty template. I'm just going to duplicate this file. Hopefully you can read this all right. Just let me know if it's okay for you. And what I'm going to do with this template, I'm going to rename it to WITSML reader. Okay. So what we want now, it's open this file. So this project is going to be reading and plotting well trajectories. That's what we're going to do with this one. And for the libraries, we're going to use effectively just a couple of libraries. So we're going to use Welly. And we will also be using Matplotlib for the time being. So let's import those couple of libraries. I'm going to leave this empty. Later on, I might put something in there or not. I'm just going to take one file. I'm going to take one of those files to show you more or less the structure of a file. And so that is the trajectory for one of the files. I'm just going to store that in here. And so let's read the WITSML. So let's do this. And remember that we can read files in the following way. I can say with, and then open the file that I want to read. In this case is a WITSML file as F. What I'm going to do is store all this information. I'm going to read that file and store this information into this variable data. So if I show you what is in data, it's very nice piece of information from that file, which as it is quite pointless to have a look at the data as it is. So one thing that we need to do is use another library to convert this data in something that we can read. So let's import that library. That library it's a beautiful soup. So from BS4, sorry, import beautiful soup. And what I'm going to specify here, now that I have read the file, I want to say, let's call this data XML. It's that beautiful soup library. I'm going to read the data, and I have to specify, if I go to the documentation, I have to specify which markup I have for that data. In this case, it's XML. And let's see what happens there. I think nothing, we won't be able to see this, but still in a format that we cannot read. But we can do some other stuff now that it is in that format. One thing that we can do is use some keywords. Let's have a look at what we can do with this library. hold on a second, it's doing something. Just want to explore what methods and what classes and what variables we have to that we can use for this library. It's taking a bit of time, so I'm going to actually use it straight away. This is find all, and we can list with find all. We can list all the keywords, all the tags that are available in the file. It's quite large. Let's put just to bring the unique names from those tags. So just a second, I have a message. Sorry, it's someone is if someone is writing in the chat, I'm trying to see the chat in the other window, and it's quite slow at the moment. So is this directory file located on a website somewhere? Okay, yeah. So where is this file located? As I mentioned, there is a background on this session. We are talking about the Volve data set. And the Volve data set, if you have a look at the video from the last weekend, we explain a bit of where the data is located. So the data, you can go and download the Volve data set from the Equinor website, and I believe that they have this official website where you can download all the data. So when I was showing the folder with the actual data, this is the folder that I downloaded. So any of you can go and download this public data. Does that clarify the question, Mike? Okay, good. Yeah, just stop me at any time. Ask me any questions. I feel much better if you ask questions along the way. Right. So moving on. I'm just going to try to extract some of the tags. Let's see if I can extract some of the tags with a set and using a bit of list comprehension. I want to extract for the tag name or tag in all this messy data. Let's see if we can do that. And let's say this is a string, by the way. Okay, now this is more the kind of nodes that we have in the data. We have azimuth, we have dogleg severity, inclination, and so on. So there are quite few information in that file. And this tells you very quickly what you have and what you don't have. So let's add another line here. And if I want to bring, for instance, let's read that data XML. And I'm going to bring .find all, but I want to bring only the azimuth, for instance, which is, or let's take a TVD, the true vertical depth of a well. So I want to bring the true vertical well of a well. And you see that I have now here a lot of nodes with true vertical depth. So if I print, let's call it DVD temporary TBD. So if I list how many of those nodes I have 114 nodes. So if I go to inclination, same amount of data. So if I want to extract from TBD, from let's say from this data, I want to extract any value. I can go, for instance, this is a list. As you can see, it's a list of let's say of tags in the XML. So if I want to extract more values, I can just say I want to extract let's say I want to extract the third value, which is index number 2. And I want to, if I do it like that, I just have I just have the whole tag. So just for you to understand what is this type of data, and also for, so this is a tag on that beautiful SOAP XML. So if I want to extract the actual value, I can convert to text. Okay, I can extract the text that is in that file. So now you can see that after executing that, I can extract pretty much any particular value from this data, and that's quite useful.
Hello.
Yes.
Hello, sir.
Yes.
Yes. So my question is like, can we just convert this data file to pandas so it will be easy for us to work upon that?
We're getting there. So first we need to read the data, and then we're gonna read it into pandas.
Okay, sure. Thank you.
Okay, cool. So yeah, so we have to very slowly get in there, and so if I want to, which is the next point, if I want to transform all this data, actually, let's only bring, for instance, the last point, and let's convert it to text. That's what we have in the last point. And let's create a pandas data frame, exactly as our friend mentioned. Beautiful Soup is not part of let's say native Python libraries. You can install it with as you can install any other libraries with pip install beautiful BS4. You can install it as with pip install with pip. So let's create a data frame, and for that I will need pandas. So import pandas as PD, and PD dot create an empty data frame, and let's create the first. I'm going to create. I'm going to extract few values, and I want to extract. Let's see which columns I want to extract. Let's say that we want to extract from all these values. I want to extract azimuth. I want to extract MD and TBD for the time being. And I think let's extract inclination. I think that's, yeah. Okay. So of course I can do something like azimuth. And to answer the questions, yes, we're going to extract. How we can extract that? I'm going to extract it with a list comprehension. So I want that text that I have here. So I want to convert that text to a float. So I want to convert that text to a float. For x in, and let's use this with azimuth. Okay. For each value in azimuth, what I want to do is extract the text, and I want to convert that to a float, and I want to store it in that data frame. Yes. So if I see what I have in the data frame, as you can see, I have the azimuth. Now I want to do that for all the columns. So let me do something like for column in columns. for columns in columns. I'm going to do then column here and column here. See if that works. Right, here we go. So we have azimuth, MD, TBD, and inclination. Right. So is that, does that answer the question? Yes, no? Right. Okay, so now I want to really, sorry, that's my mobile pinging. So now I want to bring a lot of files. I want to bring all the trajectories in all these folders. So I want to extract it from this root folder. I know this, my root path is this one. Right? And also I know the list of all the wells that I want to extract. So I know I have all the wells, all these wells in different folders. I'm going to use a prefix sort of word to, and the suffix, let me copy this. So I know that the root it's going through the WITSML real-time drilling data inside my Volve folder, and I have another set of folders as you can see here that I want to go through. So it's a simple for loop through all those folders, and I want to extract the first XML in those folders that usually has all the values aggregated. And the next thing that I want to do, it's iterate through all these. So for in wells, I want to build a data frame like the one above, like the one that we were showing before. But also we would like to probably add here the name of a well. So let's define the same, probably use another data frame. Let's use a data frame for all wells. And we have to pretty much do the same that we did here, yes? So what we want is read all those files, okay? So for all the wells, I want to read some sort of WITSML, and that new WITSML, it's basically the path, the whole path, plus the prefix, plus the well, plus the suffix. So I'm going to iterate through all that. Open all those files, and I need to use a beautiful soup to parse all those files as we did it before. So we use beautiful soup. For all the data in the WITSML, we're going to use beautiful soup, and let's store that in the data XML. Sorry. Data underscore XML equals to this. So I should have that file, and the only thing that I would need now it's to do this bit. So defining these columns, I want to get all the columns in that file. Of course, now let's create a sort of internal data frame, so I can hold only one well at a time first, and then we can concatenate all the data frames. So pretty much what I'm doing, it's the same thing that I was doing before. I'm reading each file, and I'm going to iterate over all the XML to get the columns azimuth, measure depth, true vertical depth, and inclination. And finally, I would like to add a column name with the name of a well. That's going to be important later on. So that's the name of a well, which is well. So far so good, but this is inside a loop, and I want to store all in a pandas data frame with all the wells, all the azimuths, measure depth, inclination, and so on. So in order to do that, I can use pandas concat, and I can use df all wells. On the first iteration, it's empty, and then go to the second iteration. And I believe that I need to put this and tell it that it has to stack it on the columns. Let's see if that works. It's doing something, seems to have done something, I don't know. Let's see if I have something here. Nothing. The F all wells. I think I need to ignore the indexes here. What's happening here?
But why don't you try just one and see if it works with one data frame? We go from there. Or...
Yes. Oh well, let's hold on a second, because so we are reading here the data XML. Yeah, let's print df here for a second.
Yeah, print the head then.
Yeah, so far it's loading, so I have all the wells. Oh, of course. I need to store it. I need to return. There we go. Let me remove a print. Okay. Now we've got all the wells with azimuth, measure depth, TVD, and inclination plot there. And what I'm going to do, it's just to finish this exercise. It's quite short. It's really simple to do it. I'm going to use a Plotly Express to have a more like a 3D visualization rather than like a 2D plot. So I'm going to import Plotly, and I'm going to import Express to be able to plot in line here. So one thing that I forgot to import here that would be very useful. It's I can import from the vectors the actual northing and the actual coordinates of a trajectory. So I can import the displacement in the north direction and the one in the easting and the northing. So if I do that, is it EW, sorry, north-south EW. And if I do that, let's read again all this. So I have now that displacement. And this is important because now I can have a plot with Plotly. I can do something like figure, and I'm going to use that library that I just imported. And there is a functionality for 3D lines. The only thing that I need to do is specify the data frame that I want to plot, what are the X, Y variables that I want to use. So for X, I want to use this NS, displacement north-south, and for Y, displacement is west. And then for depth, I want to plot the true vertical depth. And I also have to specify if I want to split all this in multiple trajectories, I also have to specify which column has the tag. In this case, the tag is a well name. So if I run that, nothing happens. I think I need to do figure show. See if something happens there. Whoa. And they are all the other way around. And that's fine. I'm just going to do a small change here. So I'm going to create a negative TBD, which is equal to TBD times -1. And I'm going to plot that negative TBD here. There we go. And it's a nice image that I can move around, and I can probably create a new port for this output. Let's put it here. Actually, let's put it next to my code. Okay, so I can have a code, and I can have the trajectory. So I have a labels, it comes with the labels. So it's a quick one on the trajectories. I think last time I was reading the PDF, so I think this is a bit more useful. So next on the list, actually, before I read the production logs, which will lead me into this big step, let's swap this around. And I'm going to show you the pressure from the MWD. So far so good. Any questions? Okay, so let me crack on now with the pressures from the MWD. And let me show you first the MWD data. The MW data, it's inside the well logs. And there is a pressure folder. So far so good, thank you, NSA. Is that the real NSA? Having a look at my meeting, that's quite encouraging. Okay, so this good, thanks. Okay, so this is the report of the measure while drilling the pressures, and what you have here, it's briefly you have quite few stations, and basically we are while drilling the measure while drilling tool stops, pinches the formation, and then start to measure the formation pressure through multiple extractions of the certain amount of volume into a chamber that is inside the tool. So in this case, the start of a measurement, it's measured, it's accounted. Then we have a measured depth, a true vertical depth, and we have the actual pressures that are read. So this is the interpreted information. For the sake of kind of using Python to extract data and to show you what else we can do to automate data, I want to get to these plots. And potentially, if possible, I want to get to a point where I can get the pressure information. And so how we can get to this plot and where is this data? So this data is located in multiple files. And so these multiple files are in the last format. The only difference is that instead of depth, we have time. And why do we have so many files? Because we have 13 files for every pressure station at which we are pinching the formation, if that makes sense. No? So if going back to that table, and you can see here we have like 13 points of pressure. So going back to that table, we can pretty much automate this whole report by reading the 13 files and extracting and identifying all this information, right? I'm just gonna do part of it because, to be honest, for this session, I only managed to do part of it, and the logic of identifying the point, I'm still working on that. And however, it's something that anyone else can do on their own time, and if they had any. So again, I'm going to start with an empty template. Just going to duplicate this file and rename MWD pressure, and this is for this session. And actually, this is also for the session, so I can share it later on. Okay, so let me close these two files. We only need this one. And what I want to do here, just to be clear, I want to read and plot pressure data from MWD file. It seems all points are good stuff. Press in real med you wouldn't have all the stations as good as stabilized press. You will have some tight loss. Oh yes. That's a very good point. Actually, in fact, let me see this report. Yeah. So in this particular survey, you have the three pressures. So this is as someone pointed out, as Zico pointed out, we have pretty much a good connectivity, good mobility across all the formations. But there is another report. If I show you this report, for instance, you will notice that this report, actually, let's work on this report, because you will notice that there are some NAs here. It meant that the pressure, it was not able to stabilize we're not able to extract further measurements or further drawdowns for the formation. And in fact, if you can see this is quite what you would expect. You extract some volume, then after you extract some volume, the pressure response is stabilized, and you get the last stable pressure. But as it was pointed out, if in a tight reservoir, this is getting a bit more tighter. And you can see it's tighter because as you produce this drawdown, that's fine. It takes a bit longer to actually stabilize. But not only that, it's almost impossible to draw down further volumes from the formation. And on the last one, there is only a chance to take only one just a tiny bit of volume that was extracted and producing this drawdown. Then the build up just actually took almost the whole time. The whole time the tool was in the well to get back to this pressure. Probably it's not even the reservoir pressure. So it's a mini build up. So it's quite a few formations, and this one has some tight formations while pinching. Thank you, Chico. Let's have a look. So we're going to read and plot the pressure data from the MWD file, and that's as far as we're going to do. I'm going to leave you to do something more if you want. So for the libraries, let me see here. So for the libraries, as usual, we're going to use LASIO for this one. So LASIO, I tried to use Welly to read the last files, but I couldn't. So I wasn't able to read it with Welly. So I'm going to use LASIO, and for the files, I'm going to use this file here. Only one file. So step one is going to read files or read file. And it's quite simple. So I can use let's run LASIO. So I'm going to import that file with LASIO. So let's see, file is not defined. Of course, I have to run this. Module object is not callable. I think I need LASIO. I need to access some of the functions in LASIO, so I need to access read. Okay. Now, if I check what we have in there, so we have a LASIO last file, and we can access the keys that we have in that file. Yes, anyone has a comment? Hello? Okay, I'm gonna carry on. So these are the keys that I have in that file. And I can straight away produce a plot using Plotly. So another library that I will need here. So let's import matplotlib by plot as plt and plt.plot. And so if I want to plot, for instance, let's produce one of these plots, which let's go back to a report. And I want to produce, for instance, these two. So one is pressure and the other is volume versus time. So I can do las, and let's get the pressure. Oh, press, sorry. Right? And the other is a moduli, which is, you can see when it's more clear when the pressure actually stabilizes. So that's fine, but we want to really load all the stations. So we want to bring all the values and all the stations. So the way I'm going to do it's first of all, let's actually put a small comment here. Let's collect all the files. Let's collect all the last files, right? So I'm going to collect all the files here, and the way I'm going to do it is I'm going to specify in which path those files are located. So I decided that I'm going to read that well from this report that I was showing previously, okay, which is in this folder. So that well is a 9F1. So let's read that folder. And I know that the root name of the file, it's this one. So as before, I'm going to put here a prefix. A suffix, I'm going to specify dot last. Okay, I think I need an underscore here. And I want to read the number of files. It's a number of stations that we have in here, and as I think we saw that there were 6 stations. So n underscore files equals to 6, and for I in range n files, I want to append here the name of a file, which is equal to path plus prefix plus I plus suffix. Probably someone is jumping and saying, oh, that's going to fail. Yes, that's going to fail because this needs to be cast to a string. Yeah, because I it's an integer and we need to cast it to a string. So now I should have all the files right in there. And so let's do a quick plot. So I want to first for every file I want to produce this plot. Let's start with that one. So for file in files, what I want to do it's I want to do this plot. So I need to read the file and produce a plot. That's all. So use Lazio to read that file and then plot this. And see if that works. The system cannot specify. NOx pressure. I think, oh, okay. Yeah, I don't think there is a file 0. So actually, this has to go from 1 up to n plus files plus 1. So it goes from 1 to 6. Okay. So let's see if that works. Ew, that's awful. So if I want to produce a plot, an independent plot, so I'm going to just show every time I iterate through the files, I'm going to produce a plot. And there we go. Now I have all the files. Now, just to make it a bit more interesting, what I'm going to do is produce a plot that is split into into 3 sections. Okay, so we're going to have one plot with pressure, one plot with volume, and one plot with a module pressure data. And for that, I think I need to create independent plots first. So let's create a subplots for every one of the files. I want to create a figure with 1 row and 3 images. And I want that figure, let's set up a size of, probably not so big, 10 by 8. And there should be a tuple. Right, so instead of axis plot, instead of a PLT plot, I want to do axis. So for the first axis for 0, I want to produce a time, and I want to produce something different than that one. Just let's do this 3 times. 1, 2, and 3 times. So I want to do DD volume, DD press, and that doesn't work. So plots is not defined. So plots is not defined because I need to use PLT subplots. Sorry, PLT subplots. Index 2 is, oh, it's 3 plots I need. Oh, that's terrible. Is this one? It is fine. You see? No, it was not one. 10. So actually 5. There we go. So now I have the plot from every one of the stations. And I can add a bit of titles to this if I want. I'm just going to the title for the volume, just for the fun. Set title, and this is volume. And actually, let me put which station is this one. Volume. I'm going to enumerate this. And this is volume for station 1. So it's volume for station 0, which actually it should be for station +1. Volume for station 1, volumes for station 2, volume for station 3, volume for station 4, and so on. So I think the next step will be to extract the actual volumes, and I'm not going to do that in the session, but there are a few ideas that you could do. So actually, I don't know if people would like to throw some ideas of how you would extract. If you see the report, what we want is to get these points, the last point of a stabilization of a pressure for every one of the 3, say, volumes extractions in the tool. Anyone can make suggestions? So maybe, yeah. So we want to get, as the pressure stabilizes, we want to get this point, so I can produce that report automatically. So it's either by having a look at this property and see when it stabilizes for every one of the volume extractions. Suggestions? No? Subset the press data based on drawdown and report last row on every DD, right? And how would you subset? How would you split the drawdown? Because now you have 3 drawdowns. So what you're saying is that you have to subset. So somehow automatically you need to split this data in 3. But that's a good point. That's a good point. That's a very good point. So the question is how we can subset this in 3. That's a good one, Jiku. So one thing that I was trying to do, and it's sort of similar to what Jiku was proposing. I'm going to show you here. I'm not going to go through the code, but I have here identifying almost like the ranges. So I have a full range which I can identify, and yes, as you mentioned, we can extract the last point. So it's a matter of almost identifying. I have this sequence of values, and if I don't have much more values in the sequence, then I need to remove. I can split that into a second set. So where it gets complicated, it's in a data point like this one, where I can by mistake identify more extractions than what actually are in reality from the tool. But yes, I was aiming to something like that, and I'll try to see if I can split this further. Okay, thank you, Jacob. Yes, stop offline. And we have to talk about the material balance for cold bed methane as well. Need to continue on that one. Right. So just a couple of ideas of what we can do with that. And yes, so that's it for this exercise. I think the last time I was also talking about, yeah, how can you, for instance, make this automatically generate all this in different colors. And there is a library called well, not a library. Inside Matplotlib, there is something called CM or color CM. I'm not sure what CM stands for, but from PyPlot, actually, if I have already PLT there, I can do something like let me add here plt.cm, and I can generate some random colors with a function called rainbow. So in this case, I'm going to generate let's put together a list of values. I want to generate five values or 6 values for how many stations do we have here? We have 6 stations. And I want to store this in color. So if I show you that, what is color? So I have an RGB set of colors with some sort of opacity in here. So one thing that we could do is, as we iterate through this, we can also set the color through I. So that's color equal to color sub I for every one of the plots. It's going to be a bit of a carnival, but just giving you some ideas of what you could do with getting some different colors there. What's happening there? 0, 1, 2, 3. I'm not quite sure what's going on in there, but I think you get the idea. Not quite sure why this is changing. This is not changing. That's fine. Not gonna be further. Okay.